now for what many people consider to be the most difficult section of the entire course. Now, I'm not trying to scare you. In fact, I really like stoichiometry, and some people find that they really enjoy this as well. But the critical part here is that we're going to be chaining together multiple sections that we've been discussing. So this includes balancing equations, molar mass, and just the whole concept of dimensional analysis, or the domino method. And so again, don't be worried, but it's just going to, take a little practice, and you're going to have to kind of slow down and really think your way through these. So to give you an example, what stoichiometry is like, it's a lot like making an impossible bottle. I really like impossible bottles. Growing up, my dad had a ship in a bottle sitting on the shelf, and I always thought that was the most amazing thing, and I would always wonder, how in the world did he get it in there? Okay, and he never told me. But it turns out that, when I grew up, I wanted to, a couple of years back, I thought, you know what, I want to make something in a bottle as well. Now, because I like card tricks, I decided to put a deck of cards into an old acid bottle from the lab. And, it does actually have the cards in there. All right, I did a couple more. So tennis balls and a pine cone. Here are some larvettes. These are the dried mealworms. These are kind of tasty. They taste like Fritos, actually, so they're not bad. But I put these into a bottle. A Rubik's Cube, mostly because I can never actually figure out Rubik's Cube, so I just stuff it into a jam jar so that no one messes with it. Last Easter, my kids got a bunch of these Bertie Bott's beans from Harry Potter, and they would sit there and try to feed me the nasty ones. And after eating one of the vomit-flavored ones, I vowed I will not let them have these again. So I went ahead and put the entire box into a small bottle, just to protect myself. And then my last one, you can see here, this is, I call it everything but the kitchen sink. It's got 2 decks of cards in there, a box of chalk, a huge bean bag, and a baseball, and a bottle of glue, a box of matches. It's got a paperback book in there, everything in there, right? So the question is, when you're making an impossible bottle, how do you actually do this? Well, it's all available on Google. You can find anything on there. But it turns out that, the rule is you have to make everything go through the neck of the bottle, right? So everything has to slowly fit through there. No cheating and cutting the glass open or anything, which means that you need to somehow figure out a way to, to force things through that opening. So in the case of like a deck of cards, you could open the box, take out the cards, carefully roll up the box, put it back into the bottle, open it back up, glue it all together so it looks all pretty, and then slowly, one by one, kind of thread those cards through the neck of the bottle and put them into the box. Now, it seems like a lot of work, and it is, right? It can take hours and hours to do something like this, and especially if you're not very good at it like I am, because I definitely lack in this department, but I think it's kind of fun and amusing. And anyway, so this is a lot like stoichiometry. In stoichiometry, you're going to be doing something that looks impossible, going from grams of one substance into grams of some totally different substance. But the trick is that you have to kind of slow down and convert everything into a form, in this case moles, that you can actually use. All right, so that's kind of the key there, is that we are going to convert everything into moles and then do a balanced equation domino, or a mole to mole ratio, depending on which textbook you're reading. And then that's going to allow us to do something that looks pretty incredible, and it really is. So what's the technical definition for stoichiometry? Well, I always say that stoichiometry is Greek for a whole lot of fun, but actually stoichiometry means the study of the numerical relationship between chemical quantities and a chemical reaction. Okay, what does that mean? Well, it means that we're going to use the law of conservation of mass and a balanced equation, and we're going to figure out, if I have 10 grams of methane, how many grams of carbon dioxide can I produce? And we're going to, again, use this balanced equation, and it's very important. That's why it's underlined. I'm also going to go ahead and just, underline this a few more times because it's that important. You must have a balanced equation, okay? So the number one thing you should do whenever you see a stoichiometry problem is look at the balanced equation. Is it balanced or not? If it is, great. You can go ahead and just go straight into the problem. If it's not, then you have to balance it, because otherwise you will go through a lot of work, this huge domino problem, and you'll get the wrong answer. So make sure it's a balanced equation. So let's actually start out by looking at what a balanced equation really means. A balanced equation is a lot like a recipe, right? Let's say that you look up some recipe online and it's for pancakes, right? And it says that if you have a cup of flour, 3 teaspoons of baking powder and 2 eggs, it will make you 5 pancakes. Okay, that seems pretty nice. But it turns out that even without thinking about it, we are interpreting these values, these parts of the recipe, as actual conversion factors. What this means is that if I have 1 cup of flour, I'm going to need 3 teaspoons of baking powder to react with it, right? Or if I have 1 cup of flour, I need 2 eggs, right? Assuming I have plenty of the baking powder. Or if I have 1 cup of flour and plenty of everything else in the reaction, I can make 5 pancakes, right? And so this is kind of a natural thing that we do. In fact, let me give you a problem that you probably run across in the kitchen. Let's say that you have 10 eggs, right? That's what we're always running out of at my house. We usually have lots of flour, lots of baking powder, but we run out of eggs, right? So if you have 10 eggs and you have plenty of everything else, how many pancakes could you make? Well, in order to work this out, you need to go back to the recipe, which says that for every 2 eggs that you have, you can make 5 pancakes. Again, assuming you have plenty of everything else. Okay, so what does that mean? Well, we could actually just look at it, and you might be able to say, well, let's see, 2 eggs gives me 5 pancakes, so 10 eggs is 5 times that, so I should be able to get 25 pancakes. And you'd be right, but let's actually work through this, and let's see how you could set this up as a domino problem. So what I would do if I were setting this up is, again, just like always, I have a box in the top left corner and a box in the bottom right. Now, I know that I have 10 eggs, so that's what's going to go in the top left-hand box, and my question mark is pancakes, right? Just abbreviate it, pan. All right, so we've got 10 eggs. Now, this thing right here is a domino. It's a conversion factor that's going to go here in the middle. Now, where do I want my 2 eggs? Do I want that top or bottom? Well, it turns out that I actually want that on the bottom, right? Because that way the eggs will actually end up canceling each other out, which means that I need 5 pancakes up on top. Because just like always, I have to use both sides of the domino, right? Both sides of this conversion factor. Now, I can go ahead and check to make sure that everything cancels out. So notice the eggs cancel, top and bottom. Pancakes cancel, top and bottom. Everything has canceled, therefore I know I've set up my problem correctly. And just like always, multiply all the numbers across the top, then all the numbers across the bottom, and then divide top over bottom. So 10 times 5 is 50, divided by 2 on the bottom. This comes out to 25. And what are my units? Well, my units are going to be pancakes. So just like we said before, we figured it out in our head before, right? And we naturally do this in the kitchen. We double or triple recipes. We look at, what we call a limiting reactant in chemistry, or, in this case, our eggs is what's limiting how many pancakes we can make. And, we can figure out pretty easily how many pancakes we can actually make. But it seems like once we actually get to chemistry, then people start to freak out, and they're like, oh no, it's talking about moles of ammonia instead of pancakes. I don't know what to do. Well, it turns out it's the exact same process. We just have to look at the balanced equation. So now let's actually go in and look at one of those chemical recipes, right, or a balanced equation. And let's look at it in terms of what we had just learned about a regular recipe. So in this case, our recipe says that if we take 2 magnesium and 1 oxygen, right, because remember that if it's not written, it's implied that there's a 1 there, right, for the coefficient. So 2 magnesium, 1 oxygen, we will get 2 magnesium oxide. Now we can think of this in a couple of ways. If we're talking about just molecules, I can say, well, if I have 2 atoms of magnesium, 1 molecule of oxygen, I can make 2 molecules of magnesium oxide. Or, since we often count things in moles when we're talking about chemistry, we can say that 2 moles of magnesium plus 1 mole of oxygen will yield 2 moles of magnesium oxide, and that's perfectly valid as well. So just like before, we can write this as a set of conversion factors. For every 2 moles of magnesium that I have, I'm going to need exactly 1 mole of oxygen gas to react with this. Or if I have 2 moles of magnesium and lots of oxygen, I will make exactly 2 moles of magnesium oxide. Okay, so this is the exact same thing we've been doing with the recipe, but now we're just looking at a balanced equation instead. So let's go ahead and try a calculation with this. So the question says, how many moles of magnesium oxide can be formed from 8 moles of O2? All right, so how do we do this? Well, just like always, we're going to set this up as a domino problem. Now, notice the problem says how many moles of MgO, right? So question mark moles of MgO. Notice that I'm specifically writing out moles of MgO, not just moles. This is pretty critical because we're going to be using moles of oxygen and moles of MgO in this equation, and we need to specify which is which, right? So it's a good habit to start getting into to write moles of NaCl or moles of lithium or whatever your moles are. So what's the number that we're given in the problem? Well, we're given this number here, 8.0 moles of O2. Okay, so far so good. Now what goes here into the middle? Well, we're actually going to go ahead and we're going to pull the coefficients from our balanced equation. All right, so on here, on our problem, the first thing we need is, notice that it says moles of O2 up at the top. That means that the bottom of this domino needs to say moles of O2, right? It's the only way to make it cancel. And over here in our box we have moles of MgO, so that needs to go on the top. That way, again, it will cancel. But where do we get the numbers that go on this balanced equation domino? Well, those numbers are going to come from the balanced equation. That's why I like to call this a balanced equation domino. Okay, it's a terribly original name, I know. Okay, so a balanced equation domino. Some books will call this a mole-to-mole ratio. Some books will call it other things. It doesn't really matter. But so these numbers come from our balanced equation. So here we have MgO. Let's go ahead and look in our equation. Here's MgO. It has a 2 in front, which means I need a 2 on the domino. All right, here I have O2. Okay, here's my O2. There's no number written out front, which means it's implied that it's a 1, so I need 1 mole of O2 here. Now all I need to do is go ahead and double check that moles of O2 cancel moles of O2, moles of MgO cancel moles of MgO. Everything cancels, which means I know I've set this up properly. So 8 times 2 is 16, divided by 1 is still 16. So I have 16. My units have to be moles of MgO. And notice that I started with 2 sig figs, so I end with 2 sig figs. So this is my answer here. Remember that these numbers here on the balanced equation domino, these are perfect counted numbers, right? These are kind of definitions that 2 moles of MgO come from 1 mole of oxygen. All right, so we don't need to worry about the sig figs in there. We have unlimited sig figs in our central domino here. So all we're doing is counting sig figs in our original number and giving that many sig figs to our final answer. So also notice that in this case we converted between moles of MgO and moles of O2. So we went from a reactant into a product, and that's perfectly fine. But in another problem, we could easily go from one reactant into another reactant using those coefficients there, or we could go from one product into another product if we had 2 or more products. We can mix and match however we want. So we really don't care where the coefficients come from. For this domino here, all that matters is that if it says MgO, you look for MgO in the equation. If it says O2, look for O2 in the equation. Now let's practice again. Let's go ahead and look at this equation right here. All right, so in this equation, first thing I notice is it's not balanced, right? In my last equation, it was already balanced, so I didn't need to worry about that step. But in this case, it's not balanced. So before I even do anything else, I'm going to make sure that I balance this equation. So let's see. I'm going to go ahead and write a little chart over here. I have carbons on both sides of the arrow. I have hydrogens on both sides of the arrow. And again, you don't need to write out this little table if you don't feel it's necessary. That's totally fine. So let's take a look at this. And I have 1 carbon on the left-hand side, and I have 1 carbon on the right-hand side, right? As you can see here. Now what about my hydrogen? It looks like I have 4 on the left. I only have 2 over here on the right, so I'm going to go ahead and put a 2 out front because 2 times 2 would give me 4 hydrogen on the right. What about my oxygen? Looking at this, I have 2 oxygen here plus another 2 oxygen, because notice this is 2 times 1. So that's a grand total of 4 oxygen on the right-hand side of the arrow. And I have a grand total, let's see, I need a 2 here to give me 2 times 2 would give me 4 oxygen on the right. Okay, so I've balanced this equation. Very, very, very vitally important thing. I'm going to go ahead and just clear this up just so that it looks all spiffy. Okay, I don't really need this anymore, so let's go ahead and erase that. Make sure I get everything. I hate it when you're like writing on the board and you leave one little tiny like niblet of marker writing on there, and it's all a pain, and I just sit there and stare at it the whole time. Anyway, enough about my OCD. So the next thing I'm going to do is I'm going to actually write in the ones, just because it kind of helps some people to remember that that's a 1 on, in front of those if it's not written. Okay, so what's the next step? Well, now that we've done all of that, let's go ahead and actually set up the problem itself. So this is going to be a domino problem. So let's set up some nice little dominoes here. And it says how many moles of O2. So question mark moles of O2 in the bottom right hand corner, and it says 7.3 moles of CH4. Okay, so there I have my my initial moles of CH4. I have my question mark moles of O2, and then here in the middle I'm going to need a balanced equation domino, right? And what does it need to say on the bottom? Well, it needs to say moles of CH4, because that's the only way to make the moles of CH4 from the top left-hand corner cancel this out. And then it needs to say moles of O2 on the bottom right-hand corner. Fair enough? We all agree on that? All right, so the next thing is I need to actually go in and look at the coefficients on my balanced equation to figure out what mystery numbers go here. All right, so here I have my O2. In the equation there's H2O, there's CO2, but the only place that it mentions O2 is right here, and it has a 2 in the front. So I'm going to go ahead and place a 2 there. I also have CH4. I look through the equation. Here's my CH4. It has a 1 in the front, so I need to put a 1 there. And again, this is why the balanced equation is important, because if I didn't balance this, I would have the wrong answer, and then it would be a big waste of time. So let's go ahead and just double check that everything cancels. Moles of CH4, top and bottom. Moles of O2, top and bottom. Everything cancels. That's good. So now my final step is to multiply. So 7.3 times 2 is 14.6. Divided by 1 is still 14.6. Now let's see, how many sig figs can I actually keep on this bad boy? Let's see. Well, I have 2 sig figs in my starting number, so I can really only keep 2 sig figs in my answer. So instead of writing 14.6, I'm going to go ahead and write 15, because that gives me exactly 2 sig figs. What are my units? What was my question mark? Moles of O2. And then that, my friends, is my final answer. Alright, so we've done a couple of problems here that where we are going from moles into moles, right? And this is pretty simple, but this is just the core of a stoichiometry problem, right? I'm changing moles of substance A into moles of substance B. But it turns out that we can actually do more than this. We know that we can go from grams into moles, or moles into grams, using the molar mass, right, which comes from the periodic table. We pull out our periodic table, add things up. That tells us how many grams is equal to a mole. So I always like to write out this plan of attack whenever I'm working through a problem. And this plan of attack tells me that if I want to go from moles of A to moles of B, I have to use a balanced equation. That's the only way to do this, right? Now, I could also expand this out, right? I could go from grams of substance A over here and change this into moles of substance A. And to do that, I need the molar mass of substance A, right? I pull out my periodic table. Let's say it's carbon dioxide. So I'd add up the mass of 1 carbon, 2 oxygens, 44.01 grams is equal to 1 mole of CO2. That allows me to change it into moles. And then I could go from moles of CO2 into like moles of CH4, something like that, and change that into moles of substance B, some completely new substance, and I used the balanced equation domino to do that. But then some problems might actually have me take this even one step further. So I could actually go from moles of methane into grams of methane. And to do that, I just pull out my periodic table, I add up the carbon and 4 hydrogens in methane, and I get the molar mass. 16.01 grams is equal to 1 mole of methane, and I can convert it that way. So personally, I find this plan of attack to be really, really useful. I'm going to use this a lot. If you don't think it's useful, just don't worry about it. But I use this a lot. So let's go ahead and try out one of these problems together. All right. This one seems a little complex, but it's not too bad. So it says how many grams of C4H10, which is butane, are needed to produce 3.2 moles of carbon dioxide. What's the very, very, very first thing we should do? Well, if you said have a sandwich, that's a great idea. But actually, while you make me a sandwich, why don't we go ahead and balance this equation? Okay, so let's see. Let's go ahead and make our little chart of destiny over here. We're going from carbon into carbon, right? We also have hydrogen on both sides of the arrow, and we also have oxygen on both sides of the arrow. Now, how many of each of these things do we have? Well, it looks like we have 4 carbon on the left, and if I put a 4 here for the coefficient, now I have 4 carbons on the right. So far, so good. What about my hydrogens? It looks like I have 10 here. So 10 hydrogen on the left. So here I only have 2, but if I put a 5 in front, 5 times 2 would give me 10 hydrogen on the right. Now my oxygen. Here it looks like I have 4 times 2, which is 8, plus 5. 5 times 1, right? Which is just 5. So that's going to be a problem, right? Because that comes out to 13. There's no whole number that I can put here that would make that into a 13, right? So I'm running into this even-odd dilemma. So what do? I double everything, right? So let's go ahead and double everything. So I'm going to put a 2 here, and I'm going to go ahead and erase all this stuff just to clear it up a little bit. Alright, so I'm going to just keep erasing all of this stuff. Okay, now, actually I'm going to erase this over here as well because we're going to be fiddling with that a bit. Alright, so I doubled the C4H10. That also means that I need to double the 4 here, right? So instead of a 4, that now becomes an 8. Alright, and then that also means that I need to erase this 5, and instead I'm going to go ahead and put a 10 here. Now, what did this do for us? Well, notice that we now have 8 carbons on both sides of the arrow, which is really good. We also have 2 times 10 is 20 hydrogens, and 10 times 2 is 20 hydrogens over here. So we've kept everything balanced, right? We kept our carbons and our hydrogens balanced. But now let's look at what's happened to our oxygen. We have 8 times 2 gives us 16 oxygen here, plus 10 times 1, which gives us another 10, which is 26, if I'm counting correctly. Alright, so 26, which means that I could go ahead and put a 13 here. 13 times 2 would give me 26 oxygen. So now I have a nice balanced equation. Alright, so I went ahead and wiped the screen clean, and I'm going to go ahead and bring this thing up because it might be useful. And let's go ahead and just rewrite our balanced equation. 2, 13, 8, and 10. Alright, so we have a nice balanced equation, which is the very first thing we need. The next step is we need to actually just set up the problem itself, right? So let's go ahead and do that now. I'm going to give myself a bit of space here, because this is going to be a bit more complex than before. So it says how many grams, right? So question mark grams of C4H10. So that's my question mark. What's the number that's given in the problem? Remember, I'm not going to mess with the balanced equation yet, but it looks like this 3.2 moles of CO2. 3.2 moles of CO2 is the number that's actually given in the problem. Now the next step I need to do is I'm actually going to go up here to my plan of attack, and I'm going to figure out where to start and where to end. So what do I mean by that? Well, notice that I'm starting with moles of CO2, right? So I'm starting with moles of substance A. So right here, moles of substance A. And then over here on the bottom right, I have grams of C4H10. So I'm going into grams. So I'm always starting with substance A and turning it into substance B. So in this case, I'm going moles of CO2 to grams of C4H10. Now notice that I have two dominoes in between these two, or two arrows in between these two quantities. So that means I need exactly 2 dominoes in between here. All right. And the nice thing about this plan of attack is it actually tells me what those dominoes should be. The first domino should be a balanced equation domino, which we've done that, right? So that's nothing new. So I know that this should say moles of CO2 down here. And then I'm trying to turn this into C4H10, right? So I'm actually going to write moles of C4H10. Now you might say, well, why can't you go straight into grams of C4H10? Well, you can't. Remember when I showed you those impossible bottles, and I said that everything has to go through the neck of the bottle? That's just like everything has to go through this mole-to-mole ratio, or this balanced equation domino. So I have to, to set this up in this way. Now notice that by writing this balanced equation domino out, I haven't actually included the numbers from my balanced equation. So let's do that now. I have C4H10 on the top. So here's my C4H10. It looks like I have a 2 there, so I need a 2 on the domino. And then I have CO2 on the bottom. Here's my CO2. It has an 8 in front, so I need an 8 on my domino. And now I'm not going to mess with that those balanced equation numbers at all. So I'm not going to mess with those balanced equation numbers anymore, right? I've done that balanced equation domino. That's it. So let's go ahead and see what else I need to do. Well, notice that if I go ahead and cancel things out, my moles of CO2 cancel out, but moles of CH4 do not, or C4H10 do not cancel out grams of C4H10. How do I go from moles to grams? Oh yeah, I have to do a balanced I need to pull out my periodic table and add things up, right? So I'm going to do that in the bottom left here. So C4H10. So that means I have 4 carbons. If I look at my periodic table, the mass is 12.01 grams for each, and then I have 10 hydrogens at a mass of 1.01 grams each. And if I go ahead and add those up, punch that into my trusty handy-dandy calculator of science, so 4 times 12.01 plus 10 times 1.01, looks like the mass is 58.14 grams of C4H10 is equal to 1 mole of C4H10. And again, I'm making sure to write out grams of a specific substance C4H10 and also moles of that, because we're going to be working with moles and grams of different things, and I don't want to get confused. Okay, so I've done that. Now, where do I want my 1 mole of C4H10? Well, I want that on the bottom, C4H10, so that it will cancel out. And then I can go ahead and put my 58.14 grams of C4H10 up on top. Now by doing this, notice that my moles of C4H10 cancel top and bottom, grams of C4H10 cancel top and bottom. And everybody's happy, right? So the only thing left is to actually multiply these together. Now notice that these are getting a little more complex. So remember that what we're doing is multiplying the top all the way across, then multiplying the bottom all the way across, and then dividing. So I'm just going to go ahead and do that in my calculator. So 3.2 times 2 times 58.14, and then dividing that entire thing by 8. So let's see what that brings up. All right, it looks like this is coming out to 47 if I round to 2 sig figs, right? So 47, because it's 46.5, so round up to 47, and my units are over here. They are grams of C4H10. And that's my final answer. So anytime you put in 3.2 moles of CO2, or if you produce 3.2 moles of CO2, it took 47 grams of C4H10 to actually do this. Okay, so I told you that these would be a little complex, but hopefully if I keep working through these, they'll make a little more sense to you. So honestly, the best way to learn this is to just work through some more problems, so let's go ahead and try that. So here's another problem. How many grams of hydrogen are needed to produce 95 grams of ammonia? Well, what's the very first thing we should do? Balance the equation, right? So in this case, we have nitrogen, and we also have hydrogen on both sides of this arrow. So it looks like I have, here I have 2 nitrogen. So let's put a 2 here. That gives me 2 nitrogen. And then it looks like I have 2 times 3 would be 6 hydrogen on the right. So 3 times 2 would give me 6 hydrogen on the left. Okay, so we have a nice balanced equation. 3, 1, 2. Okay, so I'm going to go ahead and clear that off. And let's bring up the plan of attack, right? So we're going to need the balanced equation, obviously. So 3, 1, and 2. All right, so that's the first part of the problem. Now the next part is to actually set this thing up, right? So we're going to need some space. And you'll notice that I left a lot of space over here, which looks kind of ominous, right? So what's going on here? Well, we have 95 grams of NH3. What's my question mark? My question mark is how many grams of H2? So question mark, grams of H2. So looking at my plan of attack, I'm starting with 95 grams of substance A, right? So I'm starting here, and I'm going all the way into question mark grams of substance B. So I'm going all the way over to here. So notice that I have 1, 2, 3 dominoes here in the middle. So I need 1, 2, 3 dominoes on my little domino line, right? So this is a little complex, but it's not too bad, right? Because luckily this tells us that first I need a molar mass domino. So let's go ahead and do that. How do I get the molar mass of NH3? Well, just like always, I can go ahead and add up the masses of nitrogen, hydrogen, and that's it, right? So I have nitrogen, which my periodic table tells me is 14.01 grams. And then I have 3 hydrogens at 1.01 grams each, giving me a grand total of 17.04 grams of NH3 is equivalent to 1 mole, right? Alright, so where do I want my 17.04 grams? Top or bottom? On the bottom, right? So 17.04 grams of NH3 is equal to 1 mole of NH3. Now, one common mistake that people make is that they will say, you know what, in my equation it says 2 moles of NH3, so I should write a 2 here. No, do not do that. On a balanced equation domino, that's where we look at the balanced equation. On the molar mass dominoes, it should always, always, always simply say 1 mole of whatever substance on one side and then the grams on the other. Always 1 mole and the number of grams that you added up. Okay, It's only on the balanced equation domino that we need to, to switch things up. So here, luckily enough, we are hitting our balanced equation domino, right? So what does that say? Well, it has to have moles and moles, top and bottom. We're actually going to put moles of NH3 on the bottom, so it'll cancel. And then I'm trying to turn this thing into moles of H2, or to grams of H2 eventually, but I need to go through moles. Now, what do I do for my coefficients? Well, I look at my balanced equation, right? There's H2. Oh, here's my H2. Has a 3 in the front. I need a 3 on my balanced equation domino. And then here's my ammonia. Oh, here's my ammonia. It has a 2 in the front, so I put that there. Now notice that that is the only time, the one and only time, that I actually use the balanced equation in this problem. Okay, the rest of the time, you should always just say 1 mole. Now, if the problem wanted moles of H2, I would be done. But it doesn't. The problem wants grams of H2. So how do I go into grams of H2? Well, all I really need to do is pull out my periodic table, right? So I'm going to go ahead and erase this over here because I'm going to need some space for this. So I have H2. So that's just 2 hydrogens at 1.01 grams each, which is a grand total of 2.02 grams of H2, and that's equal to 1 mole of H2, right? Okay, so now where do I want my 1 mole? Top or bottom? On the bottom. Okay, some people try to memorize like, oh, if it's in the first domino, moles goes on the top, and if it's in the last domino, it goes on the bottom. I can't do that, right? All I do is I look at this and I say, oh, I have moles of H2 on my balanced equation domino on the top, so to make it cancel, I need to put moles of H2 on the bottom to cancel it out, and that means that grams of H2 goes up here. Pull out my trusty red marking pen, and notice that grams of ammonia cancel, moles of ammonia cancel, moles of H2 cancel, and grams of H2 cancel. So hopefully you're rejoicing at this point because we've canceled out everything, which means we know that we've set up our problem correctly. Now the next step is just to multiply everything, right? So I'm just going to type in 95 times 1 times 3 times 2.02, and then on the bottom in parentheses I'm going to go ahead and put in 17.04 times 2 and hit equals. I have 2 sig figs for this problem, so it looks like I have a grand total of 17, and my units should be grams of H2. So that means that I need 17 grams of H2 in order to produce 95 grams of ammonia. All right. So again, in this problem, it took 3 dominoes, right? 1, 2, 3, all the way across. But this is about as bad as they can get, right? I mean, and this, again, once you kind of learn the ropes and learn the steps, then they're not so bad. They're kind of just like a logic puzzle. It's like doing Sudoku, where it's like, oh, if I can just figure out what's in this box. Oh, it's a 7. That allows me to figure out this and this and this. You go through the whole thing, and, it's all great. Now, if you like Sudoku, you should actually try Jigoku, if you've ever heard of that. Kind of an interesting spin on it, but that's neither here nor there. So let's go ahead and keep going with this. Before I keep going, take a quick random break to loosen up your minds a bit and watch a quick little card trick here. Okay, so what I'm going to do is I have some cards, and I'm going to go ahead and show you these cards. Okay, front and back. I'm going to give you a few seconds to memorize everything about them. Okay, so front, back. Okay, so you've got those memorized. All right, so now a couple of quiz questions. So how many cards were there? 5. Okay, you're right. There's 5. Now, what was on the cards, the face of the cards? Did you notice? Well, you'll notice that I actually had an ace there, right? Now, it's pretty easy for me to cover up the ace. It's kind of hard for you to see it, so that's okay. Let's do an easy one. What was on the back of the cards? What color? Oh, they're actually red. Okay, you should get your eyes checked if you said blue. They're actually red. Now, what was on the face of the cards besides the ace? You said they were blank. Don't play poker with me, because it looks like I have a royal flush here. All right, so just like in stoichiometry, you have to be very careful because things can change rapidly, and if you're not paying attention, it can mess you up. All right, so now let's go ahead and go back to some more chemical reactions and see if we can figure out a few more before we move on to the last little bit. Let's go ahead and try another one of these problems. So what's the first step? Obviously by now you should say balance the equation, right? So let's go ahead and balance this thing. I have carbons on both sides. I have hydrogens on both sides. I also have oxygens on both sides of the reaction arrow. Now this is the photosynthesis reaction. Actually, this is the reverse of the photosynthesis reaction that we've discussed previously. This is cellular respiration. This is where humans and other animals take in glucose, breathe in oxygen, and then literally burn the stuff and turn it into carbon dioxide, which we exhale, and water. All right, so how many of each element do we have? Well, it looks like we have 6 carbons on the left-hand side, so that means I need a 6 here, so that I have a nice balanced equation for my carbons. I have 12 hydrogens, so 12 here, which means I should probably put a 6 here, because 6 times 2 would give me 12 hydrogens there on the right-hand side of the arrow. And then what about oxygen? Well, notice that we have 6 times 2 is 12 oxygens there, plus 6 times 1, which is another 6, giving me a grand total of 18. Okay, so I have 18 oxygen on the right-hand side. Now here you might be tempted to say, well, 9 times 2 would give me 18, but you'd be forgetting that we also have some oxygens coming in here, right? So here I have 6 plus 2 times something, right? 2 times x, and I know that I need to make this add up to 18. So in order to do this, the only number that would work would be to plug in a 6 here, and so that way it would be 6 plus 2 times 6, which sure enough adds up to exactly 18. So I have 18 oxygens on both sides of the equation. So now I have balanced my equation, right? So I'm going to go ahead and clear that off and put up our little plan of attack, because that's the next step that we have. Now let me go ahead and just write in that I have a 1, I have a 6, a 6, and a 6. All right, and so this is my balanced equation. Now let's go ahead and try planning out our attack here. All right, a box in the top left, box in the bottom right. And what goes in the bottom right? It says how many grams of H2O. So question mark, grams of H2O. All right, and then what goes in the top left? Looks like 44 moles of glucose. C6H12O6. Okay, now I can figure out I have moles of substance A, so I'm here, and I'm changing this into grams of substance B over here. So how many dominoes? Oh, looks like only 2 this time. So that means I do not need the molar mass of substance A, right? If I did that, I'd be going in this direction, and that's no good. So I don't need that. Instead, I only need 2 dominoes. I need a balanced equation domino, and then I need a molar mass of substance B, in this case H2O. So that's one of the nice things about this plan of attack, is it helps you to know where to start and when to stop, right? You don't want to start throwing in random things like Avogadro's number, or like, oh, I need the molar mass of glucose in this case, and you're doing all these things. You might not need it. So just pay attention to the plan of attack, and it'll tell you, okay, I'm starting here, I need to end up here, I need 2 dominoes, and it's going to be a balanced equation domino and a molar mass of substance B. So let's go ahead and do that. First we need the balanced equation domino, which should say moles of glucose, C6H12O6 on the bottom. And on the top, what should it be? Moles of water in this case, right? Because we're trying to turn this into water eventually. All right. Now I need my numbers, right, for my balanced equation, my coefficients. So looking at glucose, here's my glucose. It has a 1 in the front. It needs a 1 on the domino. What about H2O? Here's my H2O. It has a 6 in the front. I need a 6 on the domino. Now I can put away the red pen because I no longer need it, right? That's the only time I use the balanced equation. The next thing I need is this molar mass of substance B. I need the molar mass of water because that will allow me to go from moles of water into grams of water. So to get that, I pull out my trusty periodic table and I look up hydrogen, so 2 times 1.01 grams for hydrogen and 16.00 grams for oxygen. If I add that up, it comes out to a grand total of 18.02 grams of H2O is equal to 1 mole of H2O. Remember that anytime you add them up on the periodic table, it's always equal to 1 mole, right? All right, that 1 mole is going to go on the bottom of my domino this time so that it will cancel, and my 18.02 grams of H2O goes up on top. Now I can just double check that everything cancels out. Check myself before I wreck myself. Let's see. Moles of water cancel, grams of water cancel. Yep, everything cancels properly. If something didn't cancel, it means that you flipped one of your dominoes inadvertently, and you need to go back and erase it and flip your domino the proper way so that everything cancels. So now what do? Well, now we just pull out our trusty calculator, and we take 44 times 6 times 18.02, divide by 1 on the bottom. So looks like we have 4757 grams of H2O. So a huge number. How many sig figs should we actually have, though? Well, looking at this, my first number only has 2 sig figs, so my last number should only have 2 sig figs. So I'm going to go ahead and round that to 4,800 grams of H2O. So if I have 44 moles of glucose, I can make a lot of water, right? Okay, so now for the last one. Are you excited? Okay, good. Me too. So for this last problem, this is a thermite reaction, which again is a really fun reaction that you should Google and watch a couple videos on because it's pretty exciting. All right, now let's say that you're setting up a thermite reaction and you want to know if you have 122 grams of aluminum, how many grams of molten iron can you produce in this reaction? Well, first thing we need to do, balance it, right? So I have aluminum on both sides of the arrow. I also have iron on both sides of the arrow. And I have oxygen. Okay, so I have, it looks like on the left I have 1 aluminum and on the right I have 2, so I'm going to go ahead and put a 2 there. So that gives me 2 aluminum on the left and 2 on the right. Now, iron, it looks like I have 2 here, so I'm going to go ahead and put a 2 there. So that gives me 2 iron on each side, and it looks like I already have 3 oxygen on either side of the arrow. So I have a nice balanced equation now. So far so good. Now let's go ahead and turn this into a stoichiometry problem. So, oops, there we go. Oh, okay, skipping around a bit for some reason. Alright, so I know that I have a 2 here and a 2 here, and then I have a balanced equation. So let me go ahead and set this up as a domino problem, and I'm going to need a box in the top left, just like always, a bunch of space over here, and a box in the bottom right over here. And it says how many grams, question mark grams, of Fe, of iron. Alright, and it says 122 grams of aluminum in the top left. So, let's see. I'm going from grams of A into grams of B, so wouldn't you know it? I'm being mean, right? I'm making you go all the way from one end to the other. So this is going to be 1, 2, 3 dominoes, 3 steps. So 1, 2, and 3. The first one's going to be the molar mass of A. Now this one's not as bad as you might think, because notice that all it is aluminum, just by itself, right? So if I look at my periodic table, aluminum is 26.98 grams. So I don't even need to add anything up because it's just aluminum by itself. 26.98 grams is 1 mole of aluminum. Okay? Now I need a balanced equation domino, which needs to say moles of aluminum on the bottom because I started out with aluminum, and moles of iron on the top because I'm ending up with iron at the end of the day, right? And then what about my coefficients? Well, these come from my balanced equation, right? So iron has a 2 in front of it. Aluminum has a 2 in front of it. So you might be tempted to say, well, I didn't even need that domino because 2 over 2 is 1, so I could have just left that whole thing out. Well, you could, and just from dumb luck, you'd actually get it right this time, but it's much better to always include it just to show how everything cancels out. All right, so what is my final domino? Well, it looks like my final domino is the molar mass of substance B, so I need to know what is the mass of 1 mole of iron. Well, it's just iron, right? So pull out my trusty periodic table, and it says the iron is 55.85 grams. 55.85 grams. All right, double check that everything cancels. Grams of aluminum cancel, moles of aluminum cancel, moles of iron cancel, grams of iron cancel, and everything cancels, so I know I've set this up properly. Now it's just plug and chug, right? So clear everything out. 122 times 1 times 2 times 55.85 divided by, parentheses, 26.98 times 2. And it looks like this comes out to a grand total of 253 grams of iron. I started with 3 sig figs. I'm ending with 3 sig figs. Life is sweet. All right. So that's it. All right. This is, like I said, many people consider this to be the most challenging section of the entire course. Some people really enjoy it. If you're really logical and you can kind of go step by step, or if you follow that plan of attack, then it hopefully won't be too bad. Now, there is one more thing I do need to show you, but this is kind of like the cherry on top, right? This is the easiest part of the whole thing. So let me go ahead and mention the next step. So the very last little bit that we need to discuss is the difference between the theoretical world and the real world, right? So it's kind of like when you bake a batch of cookies. The recipe always says, makes 2 dozen cookies. But do you ever actually make that much? No. That's just the theoretical yield. In theory, it's how much you could make based on calculations. But in the real world, you eat some of the cookie dough, or you burn some of the cookies, you drop some on the floor, and the dog eats it, right? Mistakes were made somewhere along the way, and you didn't actually make as much as you thought. So what you actually make is called the actual yield, for obvious reasons. So theoretical is what you get from your calculations, which is what we've been doing. Actual yield is something that you would, get in the lab. You'd actually, burn some magnesium and figure out how much magnesium oxide you produce. So typically a problem that's an actual yield problem would tell you in the problem, X amount of, X number of grams of, magnesium oxide was actually produced, or something along those lines. So to give you a formula for this, it's really simple. All you would do is take your actual yield, divide by your theoretical yield, multiply by 100 to make it into a percent, and that's when you get what's called percent yield. Percent yield is to see how efficient your reaction is. If you're only getting like 5% of what you're supposed to be getting, something's probably wrong with your reaction. If you're getting like 95, 98%, then you're great, right? Maybe you're only losing a little bit because your lab partner sneezed on it, or whatever. So let's go ahead and actually try just one problem of these so that you can see how this works. All right, so before we do anything else, what should we do? Well, we should balance the equation, right? This one's really easy to balance, so I'm not even going to bother, putting out my little chart here because, oh look, it appears that everything is already balanced, right? 1 calcium, 2 chlorine, 2 chlorine over here. So if I have a 1 in front of everything for my coefficients, it's already balanced. Woohoo, that's nice. All right, so what's the next thing that we need to do? Well, I need to go ahead and set up my actual problem here, correct? Okay, so I have my massive setup of destiny here. And let's read through the problem now. It says that 241 grams of calcium is reacted with excess Cl2, so plenty of Cl2, we don't need to worry about that, according to the following equation, which we know is balanced. If 122 grams of CaCl2 is produced, what is the percent yield of the reaction? Alright, so one thing that I'm going to pull out right away is that right here, it's telling me that this much is actually produced, right? So for my formula, I know that percent yield, well, I'm actually going to need more space than that. I can't write that tiny. Okay, so let's go ahead and try this again. I'm going to say that my percent yield is equal to my actual yield over my theoretical yield, abbreviate that, times 100. So notice that I already have my actual yield right here. So I already have that top number. Now I just need the theoretical yield, which is what I get from punching in all of my my numbers in the stoichiometric problem and crunching them and getting out a number at the end of the day. All right, so what does that mean? Well, that means do not touch this number, the 122 grams of CaCl2. Instead, let's go ahead and put in this 241 grams of calcium here. And I want to know what's my theoretical yield of calcium chloride, right? I know that I'm actually getting out 122 grams of CaCl2, but how many grams of CaCl2 should I be getting out? All right. Now looking at this, stoichiometry problem, I'm going from grams of A to grams of B. So sure enough, 3 dominoes, right? 1, 2, 3. 1, 2, 3. So the first one I need is I need to know 1 mole of calcium is equal to how many grams of calcium? Well, it's just calcium, so if I look at my periodic table, it's 40.08 grams. Alright, so that's the first step. I can go ahead and make sure that I set that up because those cancel out nicely. My next step is to do a balanced equation domino, right? So this is going to say moles of calcium on the bottom, and then moles of CaCl2 up top, because notice that I'm trying to turn this into CaCl2 at the end of the day. Now I need my trusty little coefficients, right? All of my coefficients in this reaction are 1s, right, for the calcium and for the calcium chloride. So that's good. My moles of calcium cancel. Now I have moles of calcium chloride. So my final domino, I need to go ahead and figure out 1 mole of CaCl2. And I'm not actually going to write this out, but I'm just going to add up 1 calcium, which my periodic table says is 40.08, plus 2 chlorine, so 2 times 35.45, hit equals, and this is 110.98 grams of CaCl2. Kind of running out of space there. All right, double check that these things cancel out. Moles of calcium chloride, grams of calcium chloride. So everything cancels, which means now all I need to do is go ahead and crunch those numbers, right? So 241 times 1 times 1 times 110.98, and then divide that whole thing by 40.08. And I have 3 sig figs, so I'm going to call this 667 grams of CaCl2. Okay, this number that I just figured out, that is my theoretical yield. Okay, because in theory, if I put in 241 grams of calcium, I should get out 667 grams of calcium chloride. Did I actually do that? No. If I look at my my equation, or my problem up here, it says I only actually got out 122. So let's go ahead and crunch this with the actual yield number. So actual goes on top, 122 grams of CaCl2. On the bottom, I'm going to use this, 667 grams of CaCl2. Times that by 100 to make it a percent. Notice that my grams cancel out. So I have 122 divided by 667 times 100. I have 3 sig figs, so I have an 18.3% yield on this problem. So this is how much I actually got out. Only 18.3% of what I was supposed to get out. So I should probably check what I'm doing in the lab, figure out if I spilled something or what's going on, because what happened to the other almost a little over 80% of my product. So now, just to show you something fun again, let me go ahead and show you a percent yield problem, but with coins. Okay, so as you can see here, I have 3 coins, right? Exactly 3, a quarter, a dime, and a penny. So this is my lunch money. I have 3 coins. So my theoretical yield is at the end of the day, I should still have 3 coins, right? But if you watch carefully, you can actually see what happens. If I just carefully stack the 3 coins up, and then if I just push down on it hard enough, I can actually feel it penetrating my skin. And so now, I actually only have 2 coins. Okay, the dime has completely disappeared. You can actually see where the dime has kind of entered my skin and left a little ring there. All right, so my actual yield is only 2 coins. My theoretical yield would be 3 coins. That's what I should have had at the end of the day, if not for this weird freaky occurrence. And so my percent yield would be 2 out of 3 times 100, which is about 67%. All right, so I hope you've enjoyed this detailed look at stoichiometry. If it's difficult, please let me know, and we can work through some more problems. But a lot of practice, kind of going over some more of these, and it should start to click at some point. And then suddenly you'll think, wow, this is actually kind of fun and useful, and I can do these. These aren't so bad. All right, so keep up the good work, and I'll talk to you later.